Hi, my name is Kyrene.
My name is Gisela.
My name is Marcus.
And
And
I'm
I'm
Melanie, and we're going to be talking about glaucoma and its effect on vision. We'll be discussing the normal eye physiology, glaucoma's fluid mechanics, and their governing equations, and the treatments for the disease. Glaucoma is the most common ocular disease that is responsible for irreversible blindness in the world. This is characterized by a slow increase in intraocular pressure, and the continuous making of aqueous humor contributes to this increase as the sclera cannot accommodate it any longer. The hydrodynamic resistance to aqueous humor drainage is also a reason for the increase in intraocular pressure. The resistance is due to the trabecular blockage that does not allow aqueous humor to enter Schlemm's canal, and this is significant for its endothelial lining that contains micrometer-sized openings that are known as pores.
Physiology of the eye. The eye is of spherical shape with an average diameter of 24 millimeters. It's made up of three layers: the fibrous tunic, the vascular tunic, and the retina. The muscles control the movement of the eye. The optic nerve transmits visual information to the brain. Blood vessels provide the eye with nutrients, waste removal, support, and cushion the eye. We'll be zooming into the anterior and posterior cavity of the eye, where the aqueous humor is produced. Impairment in the drainage of this fluid can lead to an elevation in intraocular pressure, which causes a disease known as glaucoma. The image on the right is an overview of a human eye with the major anatomical structures identified. What is aqueous humor? Aqueous humor is a fluid in the eye, and it performs two important physiological functions. It maintains stability of the intraocular pressure, supplies nutrients, and removes waste. Aqueous humor is secreted at the ciliary body through the ciliary epithelium. Then it passes between the iris and the lens of the anterior chamber. Once in the anterior chamber, the meshwork filters up to 90% of the fluid.
It is important to know the fluid dynamics of aqueous humor drainage through the small pores in the cellular lining of Schlemm's canal in order to understand the source of the resistance. We can analyze the flow through a single pore while treating the cellular lining as a parallel system of hydrodynamically non-interacting pores. And using Sampson's theory in low Reynolds number hydrodynamics, we're able to calculate the flow resistance of a single pore. Using the equation shown on the right, where Q is the volumetric flow through the pore, delta P is the pressure difference across the surface between locations, mu is the dynamic viscosity of the aqueous humor, and R is the pore's radius. From this calculation, a low flow resistance of endothelial lining of Schlemm's canal was predicted. The pore density and structure of the trabecular meshwork also affect the resistance to flow in this tissue. In figure 2, we can see the flow going through the unit cell that eventually goes through the pore. In many cases, glaucoma can lead to vision loss or blindness. Blindness results from death of retinal ganglion cells, and when the ganglion cell, which carries visual information to the brain from the retina, is damaged, an increase in intraocular pressure happens and it eventually dies and causes blindness. Cells need axonal transport to function, where the vesicles move along the axons by motor proteins. The motor proteins require energy that is acquired from ATP molecules, and if the ATP supply is decreased or depletes, the axonal transport would stop, which would lead to the death of ganglion cells in the primates. Axoplasm is a Newtonian fluid that is enclosed in retinal ganglion cells, and it is permeable through the cell walls. When there is a pressure gradient, the axoplasm is able to flow along the axon. The increase in intraocular pressure results in a significant axial flow of the axoplasm. Convection of the ATP towards the brain is also a result of this. And an increase in intraocular pressure values in glaucoma cause flow along the axons of the retinal ganglion cells, which depletes ATP in the cells, again causing blindness or vision loss. In figure 3, it illustrates the flow that is going through the retinal ganglion cells, and it is also affected by pressure.
Accurately measuring and understanding the flow of aqueous humor and the intraocular pressure, which contributes to the formation of glaucoma, is difficult and expensive. Therefore, to understand the flow of aqueous humor and how it can increase the intraocular pressure, computer models such as computational fluid dynamics are used to simulate the flow profiles for both normal and glaucomatous eye conditions. These models show the aqueous humor from the posterior to the anterior segment of the eye. Objects in the eye that are used in the model contain the pupil, cornea, trabecular meshwork, and Schlimm's canal. In order to simplify and get a better understanding of aqueous humor flow, these objects are assumed rigid. And Figure 4 shows a model of the anterior segment of the eye. This model uses tetrahedral mesh to ensure an accurate solution with fewer elements. Figure 5 shows a model with the iris included. For most computational fluid dynamics of the aqueous humor, the inlet of mass flow goes through the center of the iris. The equations used for modeling the aqueous humor flow include Navier-Stokes, Boussinesq's approximation, and Darcy's law. Navier-Stokes is commonly used to model the motion of aqueous humor in the x, y, and z direction. Also, using Navier-Stokes equation, the aqueous humor is assumed to be Newtonian and incompressible due to its similar properties to water. Equation 1 shows Navier-Stokes equation for Newtonian incompressible fluid, where V is the velocity, P is the pressure, rho is the density of the fluid, mu is the dynamic viscosity, and g is the gravitational acceleration. Equation 2 shows a Boussinesq's approximation where P of O is defined as the reference density, T is the temperature, T ref is the reference temperature, beta is the volume expansion coefficient, and this is the coefficient of thermal expansion, which describes how the size of an object changes with the change in temperature. Boussinesq's approximation is used due to the difference in temperature between the anterior and the posterior segment of the eye. This equation is used because the flow of aqueous humor is buoyancy-driven flow. Using Navier-Stokes equation, the Boussinesq's approximation and the governing equations consist of Navier-Stokes for incompressible flow, equation 1, and the Boussinesq's approximation to account for temperature variations in the eye, equation 2, resulting in equation 3. Equation 4 shows Darcy's law, which is used to understand the flow through the trabecular meshwork, where Q is a volumetric flow rate, alpha is the permeability of the trabecular meshwork, mu is the viscosity of the aqueous humor, and delta M is the height of the trabecular meshwork. Computational fluid dynamics models suggest that a decrease in permeability to the trabecular meshwork can increase the pressure gradient. This can lead to high levels of intraocular pressure. Figure 6 shows a graph of the permeability with respect to intraocular pressure governed by Darcy's law. Also, computational fluid dynamics show the velocity flow field of the aqueous humor, which can be seen as two counter-rotating vortices during the supine position. Computational fluid dynamics helps visualize stress, strain, and deformation of the iris and cornea. It is also important to understand that the shear stress and shear strain of aqueous humor can cause deformation on parts such as the iris and cornea. The highest area of deformation is near the center of the iris. This is believed to have happened because the aqueous humor travels in between the iris and the lens, which has a narrow cross-sectional area, which increases the velocity of the aqueous humor. Since aqueous humor flows from the posterior to the anterior to the trabecular meshwork and outcomes canal, a blockage out of Schlimm's canal will increase pressure in the anterior segment of the eye. Computational fluid dynamics modeling help us understand how a decrease in permeability leads to an increase of intraocular pressure in the posterior and anterior segment of the eye, which causes optic nerve damage that leads to the development of glaucoma. These modelings and analysis help predict the development of glaucoma, which allows for early treatment.
After the diagnosis of glaucoma, despite ongoing efforts, glaucoma is not curable. Luckily, as far as treatments, there are various ways to treat glaucoma. The three main treatments are prescription eye drops, laser eye surgery, and minimally invasive glaucoma surgery, often called MIGS for short. These treatments cannot restore vision loss that one has already experienced, but they can prevent glaucoma from getting worse. As for prescription eye drops, there are many different types of eye drop medications used for treating glaucoma, but the most common medication that is used is called prostaglandin analogs. This medication dissolves the extracellular matrix, also known as the network of proteins and molecules of the ciliary muscle. This results in the reduction of intraocular pressure and an increase in aqueous humor outflow. Eye drops are effective if used correctly, but since glaucoma is more common with elderly patients, studies show that a patient is more likely to forget to apply the medication routinely, causing glaucoma to worsen, or the eye drops are just not effective enough to help the problem. Another treatment is laser eye surgery, also known as trabeculoplasty. This procedure reduces intraocular pressure by laser beams that stretch the drainage holes or fluid channels in your eyes. Even though this helps release the intraocular pressure, patients still need to take medications after laser eye surgery. And although this treatment can be more effective than just medicated eye drops, this type of surgery is not suitable for every patient with glaucoma. If both prescription eye drops or laser eye surgery fail to work, ophthalmologists usually suggest to opt to minimally invasive glaucoma surgery because there are less risks than trabeculoplasty. This type of surgery is painless and usually a great treatment for the long run because of having to have less immediate post-operative care and leaves natural anatomy intact. The goal is to minimize the number of medications used and eventually no longer need to take medications post-op. Minimally invasive glaucoma surgery currently has 3 FDA-approved devices that mainly focus on treating open-angle glaucoma. Open-angle glaucoma is the most common type of glaucoma in the United States. They are named the iStent, the iStent Inject, and the Hydrus Microstent. The first generation device for glaucoma is the iStent. It is the first FDA-approved stent for minimally invasive glaucoma surgery. It's a snorkel-like design about the size of one letter on a penny that measures to 1 millimeter in length and 120 micrometers in diameter. The material of the iStent is made out of titanium, which is a biocompatible metal also used for cardiovascular stents. This is designed to be sturdy enough to create a pathway for the fluids inside the eye. The aqueous humor flows into the circular side of the stent, exiting out to where the pointed part is, which was inserted into Schlemm's canal of the anterior chamber. The stent shown on the top right is the iStent Inject, a second device used for open-angle glaucoma surgery. Its main focus is to drain the fluid buildup from 2 locations instead of 1. The aqueous humor exits out from multiple collector channels through the trabecular meshwork in Schlemm's canal, and this stent dimensions out to only be about 360 micrometers in length and 230 micrometers in diameter. So if you can imagine, this stent design is way smaller than the first gen iStent. It is currently known to be one of the smallest devices ever to be implanted into the human body. The third stent shown at the bottom is called the Hydrus Microstent. The design for this model is unique because it can bend to the way it is shaped inside Schlemm's canal. It can dilate the canal about 5 times the native width of the canal and contains windows that further facilitate aqueous outflow. The length of the stent is larger than the iStent and the iStent Inject, which measures about 8 millimeters in length and 290 micrometers in diameter. The material of the stent is different from the first 2 stents because this one is made of nitinol rather than titanium, although it is a type of nickel titanium. At this time, there have been no studies directly comparing the first generation iStent, second generation iStent Inject, and third generation Hydrus Microstent models altogether, according to Lam and Lawler, but they all show similar results post-op when reducing intraocular pressure. Although these different designs do not differ in results on how better either stent can be, but it can make a difference in the location of draining the aqueous humor, thus finding discoveries on how to reduce intraocular pressure in different areas of the eye. In summary, glaucoma is caused by an impairment in the drainage of an increase in intraocular pressure. The Navier-Stokes and the Boussinesq approximation equations, along with Darcy's law, explain the fluidics of glaucoma. And the vision loss caused by glaucoma can be prevented or treated by creating medical devices to aid in stopping the increase or decrease in intraocular pressure. That concludes our presentation, and thank you all for listening.